Now we'll discuss different types of explainability. We'll discuss those in the next slide. I did mention that this is one of those topics where we kind of have to jump around. It's difficult to cover this in a sequential way. So I apologize for that, but it's just it's organic to the issue of the explainability. There's this graphic here that shows this sort of unfortunate paradox that we have with explainability and model performance. Simple models tend to be they tend to paint with a broad brush. They tend to be fairly accurate, fairly they're performant, but not as good as the complex models. They tend to be very accurate and to perform very well. The irony is that the simple models tend to be explainable, whereas the complex ones tend to be black boxes. They're opaque. You can't see what's going on inside. Oftentimes, the simple ones will be called white boxes because you know what's going on. Simple ones would be like simple regression, like we've seen, or simple decision tree variations. Those are simple. Deep learning tends to be complex. You might have heard of neural networks, and we'll be discussing these two topics actually later. But they're very accurate and very powerful, but they tend to be very opaque in a sense. So this is kind of the irony that we'll be facing here as we get into this topic more. The different types of explainability, there are many. I have four here that we'll cover. It does give a good general broad sense of how this area works generally. There is more, and I should say that explainability is really quite complicated, and it's changing all the time. There's new things coming out all the time. But at high level, there's global explainability approaches. What that will do is it will tell you at a global level how a model is making its decisions. I'll give you an example. A model that is going to extend credit to someone. They're going to look at the person's background and make a decision on whether to extend credit. Things like their income level, their payment history, maybe their location, their years of education, and various other features. Recall in machine learning, we look at features that are used to help make a decision. How are those features being used? At what level do they play a role? Maybe income plays more of a role than years of education. That's what these global approaches will do. There's one called Shapley. It's called Shapley values, Shapley, named after the mathematician who came up with the approach. We will go into that at the end of this video, but that's really the goal here, is to understand the model at that level. There's also local interpretability. This would look at more nuanced and focused aspects of the global model. For example, let's say we want to look at the extending credit to people of a certain age group or a certain income range or a certain level of education. So we want to get down under the hood a bit more and look at sort of the more focused aspects of the model, which can be very unique and very shocking sometimes how they behave when you don't really look carefully. Then there's a surrogate model, and what this is simply trying to do is use a explainable model to help establish the interpretability of a complex model. So for example, we might use a decision tree to help us understand how a deep learning algorithm is working. I'll get into deep learning and some of those issues. Again, we're having to jump around here. But the idea is that the decision tree in this case, which is more explainable, or can be, is working with the same training data as the neural network, the deep learning method. And sometimes you can help determine what's going on with the black box method with something that is more explainable. It will help you kind of unpack how it's working. Then there's counterfactual, and this is really put very simply is, and this is often used with ethical considerations. Let's say that the model says that if we had a male who was making $100,000 a year and had only had one late payment on a credit card and had a master's degree, we would extend credit to that person of, let's say, $200,000. But what if we change that to female and we get $150,000? So what we're trying to do here is tweak the model, take a counterfactual position to see how does that affect the outcome. Here, of course, we were looking for bias against women. There are others, but we just can't get into them. I do think that what we have here is works quite well. And again, we're getting into some of this more as we move on here. What we're going to do now is look at an explainable model, the one that's on this slide now, and a much less explainable model, which is in the next slide, a neural network. You can see here, this is very easy to explain. If this looks familiar, it's from my unsupervised machine learning video. If you haven't seen that or don't remember it, this is very easy to explain. Over here, all we're saying here is that these are the average number of engineers working on a particular day, and this is the average number of times they're accessing a particular server. And you'll notice that the more people that are working, the often they're accessing the server. And you see this sort of nice linear relationship. This blue line that runs through the center of these data points is the regression line. It's very easy to understand. There's really nothing about this that's hidden or not obvious. You'll note that perhaps that the closer that these data points are to this line, the stronger the relationship and so forth. But this is very easy to understand. The opposite of that is what we call deep learning. Neural networks are a form of deep learning. And what happens with this is that you have over here, you have data coming in, and a decision is going to be made on the output. What happens though is there's what's called hidden layers in here. What happens is in these hidden layers, it makes decisions that we can't see. Now there are ways of pulling the data out, understanding how this works, but on its face, this is a very it's not unexplainable because these are hidden layers. There are decisions going on in these layers that we don't have access to. All we know at this point is the input and the output. It is literally a black box. So that is really the two different extremes, if you will, of explainable and non-explainable.